Hello. Thank you for giving me the opportunity to present my result. I am Mandar Tabib from Syntef Digital, and I will be presenting my work on artificial intelligence based wind and turbulence prediction at urban scale for drone operations. And this work was done under the EU CESAR funded AI for Hydra project. Regarding the contents of this presentation, I will be covering the motivations and knowledge gap for this work, the AI methodology, the results on wind and turbulence prediction by AI in terms of accuracy of AI and the computational speedups obtained by using AI, and finally the conclusions regarding the knowledge gap and motivation. Now, wind and turbulence predictions are done at different scales, and mostly these are currently done by traditional physics-based models, especially on the urban scale where we are operating. And this physics-based model take a lot of computational time. So we wanted to check the possibility of using AI for this, for predicting wind and turbulence. Now, this will be very useful for path planning and assessing dynamic airspace structure. Now, what's the methodology? The methodology involves an offline phase and an online phase. In the offline phase, we train the AI model on the big data, on the generated data, and this data is generated using computational fluid dynamics. And in the online phase, we use this AI model to infer wind and turbulence in the city segment. Yeah. Then with the case study that we have selected is the Prague city, a city segment of Prague with all the buildings and terrain in it. And we have an imaginary vertiport here where the drones will land and take off. And those buildings are about 100-meter in high in the surrounding areas. And we want to see how the drone flights will be uh, path planning will get affected by this wind and turbulence. Now, the methodology in the offline data for the offline data generation process, we first take the terrain and the buildings, digitize it, and then I created a CFD setup by using a mesh of about 8 million points, 8 million grids. And when we do the CFD simulation, we get the microscale CFD and turbulence at each of these 8 million grid points. And so 32 such CFD simulations were done. Each simulation had input boundary condition uh, comprising of wind direction, mesoscale wind direction, and associated mesoscale wind speeds. So these are the 8 mesoscale wind directions, that is the input mesoscale wind directions. And for each wind direction, 4 wind speeds. So total 32 simulations are there. And for each simulation, each input boundary, mesoscale wind direction, and wind speed, we get this flow field. And that is flow field of 8 million cells. So we have a big data set generated that is 8 million rows. That is, this is the spatial location. And for each parameters, which is the column, that is the 32 parameters, 32 set of mesoscale wind direction and wind speed. So from this big data set is now generated to unsupervised machine learning. And uh, in the unsupervised machine learning, this big data set is decomposed into basic components, two basic components. And one is the psi x, which is the dominant spatial basis patterns, which is the function of x, the spatial locations. And another is the alpha, the coefficients associated with these basis functions. And this alpha is a function of mu, that is the parameters, the mesoscale wind speed and the mesoscale wind direction. So the offline AI training gives dominant spatial basis functions, that is function of spatial pattern, and and then we use a radial basis function to regress the alpha coefficient to the parameters mu. So we have a radial basis function where we have the coefficients as a function of wind speed and wind direction. Now, in the online phase, what happens is the user provides the date and time of the day. Then at this date and time of the day on which he wants the predictions, uh, we obtain the mesoscale wind speed u and the wind direction from the weather forecasting model. And this mesoscale wind speed and wind direction is then used by our AI model to obtain the microscale flow field in the city. To obtain this microscale flow field, first we use the radial basis functions to obtain the new coefficients for the new parameters, alpha nu for the new parameters u theta, and then we use the uh, project it onto the basis functions, the spatial dominant spatial patterns to obtain the new flow fields. Now this is the toolbox that was created and provided to the consortia. They put their input day and time, and we get the output microscale flow fields. So how are the accuracy of these microscales flow field? I will inform you on the basis of the contours of deviation between CFD predicted and the AI predicted, and the relative L2 error. And so the results that I will be showing here now, they are categorized into three forms. AI during its training, how well it performs in the training database, that is already seen by AI. And but the more important factor is ability of AI to generalize. That is when the parameters are not seen by the AI. And this involves parameters in interpolatory range, that is uh, and parameters in the extrapolatory range out of distribution. So what we will see is that when we'll see the generalization ability, then what we'll see is that when parameters and the interpolatory range, the accuracy is medium and good enough to be for the model to be used. When the parameters, that is a mesoscale wind direction and mesoscale wind speed and the extrapolatory range, then it has low accuracy. So this is what the results show. First, we'll see the training performance, that is the parameters seen by AI. So it should be good, as this is how this is how the model has got trained on, and so it has to be good. So that it has trained well, you can say, in a way. So this is the results for mesoscale wind speed of 8 meter per second and wind direction 135 degrees wind direction. We obtain CFDs. This is CFD is obtaining this as microscale flow field, and this is what the AI is providing us, and the errors are very low for this turbulence field. So deviation between CFD and AI is very low. So AI has got trained well. The same way for turbulence also, the error is very low. Relative L2 error is 8.1 E minus 12. Overall error in this, all the grid points. So the AI has got trained well. But what we want to see is the generalization ability of AI. So how it performs to unseen parameters, that is the mesoscale wind speed and mesoscale wind direction, when they are in the interpolatory range but unseen. So for mesoscale wind speed of 3 meter per second and mesoscale wind direction of 120, that is in the interpolatory range, AI predicts this flow field, microscale flow field, which is similar to that predicted by CFD, and the errors margins are moderate. There you can see some errors, and these are mostly slightly higher, but in the usable moderate range. In regions where there is higher gradients. So relative error to error is still 2.7. Overall sum of errors here is on all the grid points is still low, 2.7 E minus 2. The same way we see for turbulence also. This is the AI generated turbulence microfield for mesoscale wind direction and mesoscale wind speed in interpolatory range. It is similar to the CFD generated pattern, and some errors are seen here. Uh, but overall, when you do L2 square, the errors are lower side. That is, it can be used this model. But what happens when we go in extrapolatory range? In the extrapolatory range, when the mesoscale wind direction is 9 meter per second and outside the training database and not seen, then we say that these fuel fields look very different and the errors are very high. So relative error is also very high in the extrapolation wind speed. Same way for velocity, in the extrapolated wind speed, the errors are high between CFD and AI. So AI is not able to predict it that accurately. Qualitatively, it's getting right, but quantitatively, it's very producing high magnitude. So there are high errors. So to summarize the result, as I said, velocity errors are very low in the training database. It's manageable in during for check is generalization, we can say it's manageable when the parameters are unseen parameters are in the interpolatory range, and when it's out of distribution range, it's bad. So this is the AI generated wind and turbulence here. And so to conclude, AI is orders of magnitude faster than traditional physics-based model. AI is accurate when parameters are within distribution of training database. And this is one of the applications of AI, which is not covered in the, uh, which is not for this presentation, but just a glimpse. And if we want to know about this application, it's accepted in robotics and autonomous systems. This is the AI computed real-time turbulence that is covered in this presentation. And then this is integrated it with the reinforcement learning. And we see that the reinforcement learning, this is avoiding going to the region. This is the regions of high turbulence, the red ones, and this is the regions of low turbulence, the white ones. And the drones, the RL reinforcement learning is controlling the drones to follow path that avoids high turbulence regions like this, as you will see here. Yeah. So it's avoiding path that are from the high turbulence regions. Yeah. So yes. So thank you for giving me the opportunity. For any questions, you can contact me at mandar.tabib@sintef.no. Yeah, thanks a lot.